We will learn about TCP in detail today. What is TCP? TCP is a transmission control protocol, which is a transport layer protocol in a TCP IP suite, uh, or in a TCP IP model, which is a protocol in a transport layer. There's its sibling, which is a UD, user datagram protocol, which is very lightweight. TCP is complex because it offers many services that UDP can't offer. What are the services TCP can offer? So TCP is reliable. How come it is reliable? So how it makes the data that is transmitted? How it makes the data transmitted reliable? It uses the sequence and acknowledgement number. It uses the acknowledgement where every data delivered, every segment delivered, for every segment or data delivered, acknowledgement is expected. If acknowledgement is not received, that is retransmitted. Much like we receive acknowledgement, suppose if you mail someone, let's say you asked for a leave letter. So you mailed your superior manager for a leave, and if you receive a reply, whether doesn't matter whether that reply is whether leave is granted or not. If you get the reply, that is a kind of acknowledgement. So if you don't receive the reply, let's say for the couple of days or 4 days or 5 days, what do you think? You will think inside, okay, for a couple of days if you don't receive the reply, so you might think manager might be busy, might not have seen my mail. So you will feel like it might be a good choice if I email him again. So that was serves as a reminder. Because why do you think of mailing him again? Because you haven't received any reply, whether it is granted or it is not granted, whether leave is granted or not. But suppose taken another example. You are doing a job and you are looking for you are expecting appraisal. So you sent a mail for the appraisal, but you haven't received any response from the HRT. So what do you think? After a couple of days or 1 week, you will send a reminder email. So why? Because you haven't received any response from the HR team. Approving appraisal or asking you to wait, whatever the response. The same way in olden days, in universities or for tax, if you file tax, you would have to send that copy to the appropriate destination, and they will resend another letter called as acknowledgement letter, stating that what you have sent is received. So much like that, so TCP also uses acknowledgement. TCP also uses acknowledgement such that data transmitted can be reliable without any data loss. So if sender and receiver are sender, two parties communicate each other. If the sender is sending some data but not received acknowledgement from a receiver, what it will after some time thinking packet might have lost during the transmission, so it will resend that packet again. But this kind of mechanism is not there in a UD. So such that TCP is a reliable service, providing reliable transmission service for the upper layer, such as application layer. And what else? What is and TCP is a connection oriented. It's a process to process communication. So you get it? TCP is a reliable and a process to process. It's also called end to end. Okay. So what it uses a process for a process to process communication. See what I'm using. I'm using some software here to write what I'm explaining. So this software, so when you double click that application becomes a processing memory. So likewise, if you open Instagram in your mobile, so that Instagram, so when you open that app becomes the process. So how come this TCP provides a process to process communication by making use of port numbers? Okay, so port numbers are port address numbers. Okay, it is a address in a transport layer which is used to identify the process. Okay, and TCP works much like a stream delivery service. So how it works? It provides a virtual, or it is a TCP is a connection oriented. What is connection oriented? You have the process here. Okay, and a sender computer. Okay, and you have another process here. Okay, so these two, so this processes work with application layer, and that data is actually delegated to the transport layer, TCP. You have here application layer. Application, right? And that data is, the application data is encapsulated into TCP segments, and that is encapsulated into IP segment, IP packets are, sorry, IP packet, TCP segments are encapsulated into IP packets are encapsulated into frame. But that is a story. So we are actually, we have been learning from since the beginning. Anyway, here thing is that how this looks like a connection oriented and stream oriented. This connection, when we refer to connection, this is not a physical connection, this is a virtual connection. Okay, virtual connection, it looks like a virtual connection. So what happens? So there is a process of three-way handshake. It goes to the three-way handshake and connection is established. But that is a connection, virtual connection. So once connection is established, TCP creates an environment between two processes, which seems that for those processes, it might seem, it looks like those two processes are connected through imaginary tunnel or a tube. Connection or a tube. So sending process sends data to the receiving process. And sender and receiver process are identified by port numbers, and so there are different steps, and TCP connection is established. We will see those steps, how this connection is established in a moment. And after it goes to the three-way handshake, connection is established, and these two processes, sending process and receiving processes are connected through a imaginary tube like uh, environment. So it mimics the imaginary virtual connection, and data flows as a stream of bytes through this tube or a connection. So do you have any questions so far? Hello? Do you have any questions? Okay, so I think so far so good. Let's recap and proceed further. So TCP is a reliable process-to-process communication and a stream of the delivery service it provides, and it is connection-oriented. And virtual connection, which mimics a much looks like a those two processes are connected via imaginary tube, and through which data is transmitted as a stream of bytes between these data flows as a stream of bytes between these two processes. How again this TCP packet, before we discuss, we'll discuss about a TCP header, okay, and then we'll discuss about fields in a TCP header. How this encapsulation happens? We have application data, right? What is this? Application data. And this data is encapsulated into give me a moment. Let me rewrite this thing in a better. So what do we have here? Application data, right? And this is encapsulated into it's a TCP segment, right? And we have here, what do we have here? TCP header. And it is a TCP payload, isn't it? Right? That is a TCP payload. Payload or data, don't be confused. Okay? It can be TCP payload or TCP. It is called as TCP payload or TCP data. Okay? So we have header and body. And this is encapsulated into and what do we have here? This is encapsulated into what? Hello? Are you following me? Yes. And it is encapsulated into and we have here IP. IP header. There is no head footer for the IP. Okay, so and this whole thing is IP payload. Okay, and this is encapsulated into again data link layer frame, right? Frame header. Okay, so this frame contains what is this? This is TCP header, and we have a IP header that has a TCP segment encapsulated, and IP packet is encapsulated into frame. Okay, fine. And now tell me what this, and we know that PDU, this is called, in our TCP layer, this whole packet is called a segment. This is called a segment, right? Yeah, what is segment? So TCP service takes bunch of bytes. TCP takes bunch of bytes. Bytes means 8 bytes. So 1 byte means 8 bits, and takes bunch of bytes together and puts a header to those bytes, adds headers to those bytes, and call this whole thing, this whole. So TCP takes bunch of bytes and prepends the header to those bytes, and packs all of those bytes and header together as a packet, and calls it as a segment. Okay, and this segment is encapsulated into IP payload. IP payload and IP packet is encapsulated into frame. So now let's discuss about this header, TCP header. This TCP header is quite complex compared to UDP. Okay, so let me take a TCP header from. Right? Perfect. So we have TCP header here. So TCP header, each one is called word. Okay, 4 byte. Each row is a 4 byte word. TCP header is structured in such a way that each row has a 4-byte word. Each row is a 4-byte word, which means that each row has a 4 bytes. So 8 bits are called 1 byte, 2 bytes are called, sometimes 2 bytes are referred as a 2-byte word or a 2-byte word, and 4 bytes are also referred as a word or a 4-byte word. So we have here 16 bytes, which means that 2 bytes here, 2 bytes here, which is a 4-byte word. Okay, so and which is a 32-bit word, 32-bit wide. So this whole thing is, okay, 32-bit wide, or each row has 4-byte word. Okay, so in a first row, 16 bits are used to identify the source port, which means the source process. Here we discussed this process, sender process, which is identified using the port number, source port number. And likewise, we have the destination. We have the destination port number, where destination process is identified using destination port number or a port address. And we have a sequence number and acknowledgement number. Remember what is a segment? A bunch of bytes packed together, yeah, with a header called a segment. A group of bytes, a bunch of bytes grouped together as a packet along with the header called as a segment. So those group of bytes, okay. So what happens, you know, this data from the application layer, we have here, what do we have here? We have a data, right? Data. This data, what TCP service does, takes the data from the application layer and divides into bytes and creates a packet, create a segment with a bunch of bytes and sends those segments. But to send this data reliably, to deliver this data in a reliable fashion to the destination, TCP must keep track of bytes it is sending. So that what TCP does, TCP numbers the bytes, takes the each byte, okay, and assigns a number to that byte. Okay, so that is a feature of the TCP. So each byte it takes, it assigns the number to that byte. So, but that number starts, the number, sequence number is the first byte it is sending. Number of the first byte. You understand? Sequence number of the each segment has a sequence number, which is a number of the first byte carried by that segment. So if you don't understand, let's say, let's assume that we have a 10 bytes. So each segment is carrying 4 bytes. Sorry, each segment is carrying 2 bytes. So how many segments should be, in how many segments this is just for the sake of example I'm giving you. Okay, we have a 10, so each segment has a 2 bytes. So how many segments should be sent to deliver the whole data? 5, right? Yeah, 5 segments. So these 10 bytes are numbered, okay, like this: 1, 2, 3, 4, 5, and so on, 10. Okay, but in reality, these numbers don't start either from 0 or either from 1. These numbers, sequence byte numbers, are neither started from 0 nor even started from 1. So this TCP service takes a random number and assigns that starts numbering from that random number it chooses. It may choose 2541 random number, So from here, this numbering starts like a 25, 2541, 2542, like that. Got it? So that is a sequence number. What is the sequence number? So this sequence number in each segment is a number of the byte. First number of the first byte that that segment is carrying. Let me repeat. Sequence number is the number of the first byte that segment is carrying. Okay, that segment carries a bunch of bytes. It may carry 500 bytes or 5000 bytes. So but that sequence, regardless of how many bytes it is carrying, for suppose it might be carrying 500 bytes, but the sequence number denotes or identifies the number of the first byte it is carrying. So each byte is numbered. So this numbering is independent in either both ends. So sender end may choose the random arbitrary number. Likewise, the receiver end also may choose arbitrary number for the data it is sending. So once that arbitrary number is chosen by the TCP service, that is used here to indicate the number of the first byte it is sending, which is a sequence number. Then what about the acknowledgement number? Acknowledgement number is for suppose once you have a sender here, we have receiver here. So sender sends some 500 bytes. So acknowledgement number. So once the receiver receives the data, he replies back with the acknowledgement packet with the acknowledgement number 501. Okay, so which means that I have received 500 bytes properly. So I'm expecting 500 first byte. So for suppose it is it is a 50. For suppose 50 sequence number is, so in acknowledgement packet, receiver sends the acknowledgement with the 51, which means that, so acknowledgement number indicates the number of the byte it is expected to receive. Okay, so acknowledgement number is number of the byte. It identifies the number of the byte that it is expected to receive in a next segment that it receives. So do you have any questions so far? Okay. So I hope it is clear about sequence number and acknowledgement number. So don't be confused. Sequence number is all bytes are numbered. Sequence number is a number of the in a sequence number in each packet is a number of the first byte that in a segment that that segment is carrying, and acknowledgement number is number of the byte that is expected to receive. Okay, and we have a TCP header length, which is this TCP header length, which is a 4 bits. You can see here 4 bits, and we have other 6 bits are for reserved, and we have a few other bits for flags. And don't be confused. Sometimes see, this is, we have 4 bits, and we have these are all 16 bits, and we have 16 bit for the window size. Okay. See here, TCP header length, which is combined 8 bits are described as a header length, but no, don't be confused with this. Here this is shown like this, but if you go, we go to TCP RFC request for comment. See, here it is. This is also called a data offset. So we have a 16 bits for the source port, destination port, and sequence number 32 bits, acknowledgement number 32 bits, and we have a reserved, these are 6 bits. So, and offset are 4 bits, and we have window size, which is a 16 bits, and checksum is 16 bits, and urgent pointer is also 16 bits. And you have a 40 and data and options, which can be varied from 0 to 40 bytes. So such that header is of a variable length that can be at least 20 bytes or at most 60 bytes, including options or pad. So here included, you can see here this reserved are 6 bits, and data offset or a header length, which is a 4 bits, and control bits are 6 bits. Okay. So don't be confused. Here I took it from the wiki. So here it shows 8 bits for the control bits, and it joins the both the reserved bits and header. So don't be confused with this one. Okay. So as I have shown you that in a here in a header format, this is from the RFC. Okay. So this 4 bits are. Let me take another image anywhere from here. Okay, no problem. Let's continue with this one. So this header length is of 4 bits, and this is used to identify, since the header is of variable length, we need a way to find out what is the length of the header. So for that, header length field is used. So if it is 0101, which means 5, so which means that 5 header length is of 5 watts. Or if you want in bytes, you can multiply 5 with the 4, and what you will get 20 bytes. 5 4s are 20. Okay. So same way, for suppose header is of 10, and this is here this number indicates 10. Okay, which means 10 watts. In such a case, what is the length of how many bytes it indicates? 10 4s are 40. So if it is 40, tell me how many bytes are here referring the padding or options. So you know that header is always, base header is always 20. In such a case, you have a 40, which means that you can, 20. So 20 is for options, right? So from 40, you can subtract the 20, which is a base header, what you will get the length of the options. Yes. And we have a reserved bit, 6 bits reserved. Those reserved bits are for a future use. These are here reserved. These 6 bits are reserved here for a future use. for a future purpose. There is no significance at the moment for these reserved bits. We have 6 bits for a different pointers. These are called control bits, and these are control bits are used to refer what kind of packet it is. And we have these six control bits can be set. Multiple control bits can be set simultaneously. So what are these control bits from left to right? We have a urgent, so refers to the urgent pointer, and acknowledgement. So if acknowledgement is set, which means that this packet, this segment indicates the acknowledgement. And we have the push, request per push, it is also called. And we have the reset connection. So this is this, if this bit is set, which means that it resets the connection. Okay, and we have a synchronize sequence number, or a synchronize it is referred as, which is that bit is set for the connection establishment for the first segment sent, that for the first segment during the connection establishment process, and this fin is used during the connection termination process. Okay, so these are the bits, and we have the window. So what is window? This window field is used such that it is used in congestion control, and this is controlled by the receiving window, receiving part. Receiving connection, receiving TCP connection dictates the size of the window. And we have the checksum field. This checksum field is used to use it for the integrity, use it to determine the integrity of the packet by the receiving party. So whether that packet, any of the segment is corrupted or it received intact. So this segment indicates the integrity of the whole segment. This checksum indicates the integrity of the whole segment, unlike the IP, IP header, where IP header has only header checksum, but this checksum is calculated for both header and body, or header and payload, which means that this is a checksum for the whole segment. And we have the urgent pointer, and that urgent pointer is 16-bit. So it is a valid only if urgent flag is set. Okay. So this urgent pointer is so it is not, even though some data is present here in urgent pointer, some number, it is not valid unless urgent flag is set. And we have options and padding, and we will discuss what options and why do we use padding in detail in a coming session. And that data, what this data, this is a bunch of bytes from the application layer that are placed into this segment. And this is about the TCP header. And let's close this thing with the TCP connection establishment process. How this connection is established, how it is terminated. Okay, so we have here, this is called a message sequence diagram. It is called TCP sequence diagram. It is called message sequence diagram or flow diagram. Okay, so there are different ways. So this is used to visually identify, to show visually how data or packets are transmitted from end to end. This diagram is used, and so can you see here, this is a sender process, and we have a receiving process or receiver. So how connection is established? This is called a three-way handshake. So we have the connection establishment and connection termination mechanisms in TCP. So in a connection establishment process, and for any data to flow from sender to receiver, connection must be established first. So here, first synchronize is sent. Synchronized packet, synchronized segment is sent from the sender to receiver. Okay, yeah, synchronize, which means that segment that carries no data, but the synchronized control flag is set. What receiver does once it is receives the synchronize on some random port, it can be a random port. Okay, that may be a random port number, which might be 2457. Okay, it might send a synchronize to some random port. There are what are well-known TCP ports are there. What are those? We have HTTP, which is on port 80, and Telnet on a port 23, and we have a DNS on 53 for a TCP. So let's assume this is a website. We have the port 80. So once synchronize is sent and receiver, which can be a server. Okay, so what it does, okay, if it is willing to make a connection, it will send acknowledgement. It will send a synchronize plus acknowledgement, and this receiver on the same port 2457. Okay, so let's call it as a 57. Okay, 2457. So if it is willing to, which means the synchronize plus acknowledgement, it may send two packets, synchronize one segment, another segment, another packet with acknowledgement. But to save some packets, we can send this TCP service can send a packet or segment with the multiple flags set that are synchronized and acknowledgement. And if this sender is once it receives, it waits for the acknowledgement. So the sender waits for the acknowledgement, because unless this acknowledgement is received, the sender doesn't consider this synchronize is received by the receiving party. Once the synchronized acknowledgement is sent, what sender sends? Sender sends acknowledgement. And this whole process is called, okay, this whole process, this is called three-way handshake. Okay, and after this handshake only, it is said to be connection established. Okay, so this connection, after connection established, data flows. Okay, in a two sets. And after that, we have the connection termination process. What is this connection termination process? This connection termination process also looks much like a three-way handshake. So where any party who wants to terminate the connection sends the finish. Sends finish. Fin packet, fin segment. Yeah, and what other parties are, if it is willing to close the connection, what it does, it sends acknowledgement. That may sometimes it may send fin plus sec, or it may send acknowledgement first and then a finish Okay, let's consider fin plus egg. And what this part sender does, once it receives the acknowledgement, it sends acknowledgement again, and connection is said to be terminated. Okay, let's see this flow in action. Let's see this flow in action using our let me show you that flow for a yes. This is a AAA.pcap downloaded from sample captures, and let me filter the TCP. And I have filtered the TCP and identify a synchronize. We have a synchronize. There may be multiple streams, and let me follow this stream so that only that stream of packets are displayed. Okay, so we have the second stream here, and so let's go to statistics. Sorry, analyze. Sorry, statistics, and there is a flow graph, and limit to display filters. Can you see here this TCP? Go here. Can you see the three-way handshake? Three-way handshake where synchronize sent from sending party. Sender is 1.2 and receiver is 147.2, 34.1.253. And 21 port, this is sent to the 21, which is for the 21 port is used for the 20 and 21 are used for the FTP, file transfer protocol, which is application layer protocol. And can you see the synchronized flag is set, this brackets, which is Wireshark is giving us hints, and we have the synchronized plus acknowledgement, and we have the acknowledgement. So once, after this three-way handshake, connection is set to be established and data flowed between, it is a duplex connection, full duplex connection. So data flowed in between sender and receiver. Okay. And we have here finish. Can you see here the finish, which is acknowledgement for the previous segment received, which is a goodbye. And for this, sender saved some packets by setting 2 bits here, which is this acknowledgement is for the previous packet received, and sent a fin. And sender sent a fin plus egg, which is acknowledgement is for the finish received from the sender. And we have here the acknowledgement from the sender to close the connection, and senders this server sent acknowledgement to gracefully close the connection. And we can see that here in Synec, and we can edit. Layout. Yep. So see this one. Go to flags. What flags are set here? Synchronize, which is a first. And the second one, 2 flags are set. You see, acknowledgement and synchronize are set. And sender sent acknowledgement and connection is established. And you can see here data flowed between these 2 TCP connections. And we have the termination process here. You can see here the fin and egg. And this is how it works. And you can see here for every packet sent, acknowledgement is expected, And for every packet, it applies for either both sides. Any party who sends the packet, sender, it expects the acknowledgement. Or same way, if receiver sends a reply, and receivers also expect the packet, no other party, receiver in the sense another party, who sends the reply for the data received, it will also expect the acknowledgement for the packets it sends. So this is the whole stuff about TCP so far. So what we have seen the features and services provided by the TCP, and we have seen the packet structure or format. We have seen the connection, three-way handshake, connection establishment and termination process. And we have seen what sequence and acknowledgement numbers are. We will see. And another main three features that TCP offers are flow control, yes, error control, and congestion control. Okay, so these three are important. And how this packet helps this packet, how TCP services perform these mechanisms, and how the data that is carried by the header are helpful in a flow control, error control, and congestion control. We will see in the coming session. Thank you.